Now let's talk about a derivative, which is going to be like another main concept you're going to learn about in calculus, and you're going to be doing a lot of work with derivatives and various rules involving them, and what they mean, what they can tell you, and things like that. So I'm going to kind of give you a little overview here. A derivative is essentially an attempt by a mathematician or a person looking at a function to find the slope of a tangent line that intersects that function. Okay. Now, a tangent line, that could be confused with the trig function tangent. A tangent line means that I intersect the graph in only one spot. The problem that causes with me here is, for me to find the slope of a line, I usually need 2 points of reference. And if I only have, the point where the line is crossing or intersecting the function itself, I only have 1 point of reference. I need a second point of reference to come up with the slope. So what mathematicians decided to do, they said, okay, let's approximate what this thing is. So they said, okay, let's move a certain distance away from x, that distance being h, and I can evaluate and I can find, at x plus h, the function value there. And now I have a second point, and I could use that to approximate the slope of the tangent line. But as you can see, that line, that pink line, does not anywhere near have the same slope as the red line. So it's like, well, that's they're both positive slopes, but they're clearly not the same. So they said, okay, wait a minute. What if I made h a little shorter? Well, it's going to change where x plus h and f of x plus h is. It's going to change where that point is to make the secant line again. A secant line is anything that crosses the graph in more than one spot. But if I look here again, well, it's still not the same slope as the red line, but it's closer compared to where it previously was. And if I make that distance h shorter yet, and it's hard to see here, but the line is going to be drawn here, that if I make that distance even shorter, that the slope gets closer and closer till that pink line is getting closer and closer to becoming the same slope and being the same direction and basically overlapping that red line. So based off of this, we define the derivative, or the slope of a tangent line, is given by the limit as h approaches 0 of f of x plus h minus f of x all over h, because that's how I would calculate the slope of this. Going back to the previous slide, when I look at this, I mean, usually I take my y's, I subtract them. I take my x's and subtract them. That would give me f of x plus h minus f of x all over h. That's the formula I would get by calculating the slope for this line. I get the actual tangent line slope as I let h approach 0. The reason why I'm only approaching 0 is I still need 2 points of reference to come up with a slope formula. This is a formula that we use as the first definition of a derivative. And notice that makes use of one of those things we would call a difference quotient. That's why the difference quotient was something we explored a bit before, because that difference quotient is an expression of the slope, and it's also part of what we define to be the derivative of a function. And we're going to do some more work with this, and kind of similar work we had done before with the difference quotient, to kind of do a few things with this. We also have this second difference quotient because this is a second definition of a derivative. I could say that f prime of a, where a is a real number, a specific real constant, equals the limit as x approaches a of f of x minus f of a all over x minus a. The difference is the first formula of a derivative is usually going to give me a formula in terms of x, whereas f prime of a in this formula down here would give me a specific numeric value.